Hi guys, so you're getting ready to take an embedded assessment on page 369 in your book, which has to do with some culture populations. And so I'm going to talk you through this prep page that you worked on just to make sure that a few of the critical ideas that are more of the challenging parts you have a handle on. It doesn't cover everything on the EA, but some of the more integral parts, let's say. So on this first case, you had Sonia studying culture that started at 8,000, and it's decreasing by 25% every hour. And then you're going to make a table. So if it's decreasing by 25%, there were a couple ways you could do that. You could multiply it by 0.25 and then take that away from 8,000. And do that a few times and then see where you end up, and then you could take any term, divide by the one before, and try to come up with that common factor, that decay factor. We know if it's decreasing that when we go to write a formula for this situation, that the factor would have to be less than 1, between 0 and 1 somehow. So if we take that 25% away from the whole, hopefully you came up with a decay factor of 0.75. And then you need to define the reasonable domain and range and describe the values of A and B and what they tell you. So here's what I came up with here. So the first thing I did is sort of re-explain to myself, redefine that exponential function. And then since I knew that the study was decreasing by 25%, it's 25% less than it was, less than 100% of itself. So if I take 0.25 away from 1, so this is what's making it less than 1, I'm left with 75%. So every time I'm left with 75% of what I had before. So that's the decay factor. So when you filled out your table, you could have multiplied by 0.25 and then subtracted that from 8,000. So if you took 8,000 and then you multiplied it by 0.25, you're going to lose 2,000 of it. So if you do 8,000 minus 2,000, obviously you get 6,000. So the other way to look at that is if I take 6,000 and divide by the term before it, that's the decay factor. So every time I could take my amount, multiply it by 0.75, and that'll get me what's left, 6,000. And if I hit equals, I'll get the next one. And then 0.75 times that would be this one. 0.75 times that would be this one. Now, I rounded. I decided you couldn't have a partial bacteria, so I just went for a whole number. It didn't tell us around. I just used a little logic there. So I went a little ways and found out some populations there. Then for my formula, I knew that the starting amount was 8,000, and I had figured out that the decay factor was 0.75 to the x. So for the domain and range, we know that the domain is hours, and it starts at 0 and goes up. So that's fine. The range is the culture population. Now, we know it can't go below 0. Now, technically, we know that an exponential function will never actually reach 0. So if we had the x-axis here and it starts at 8,000, it's going to go closer and closer and closer and closer, and it's never going to actually reach 0, but it's going to get so tiny that will be less than a whole, so it'll be less than 1, and I'm saying that you can't have part of a bacteria, like a piece of one. You either have one or you don't have one. So I said that we'll eventually get down to 0 bacteria. If your range said 0 is less than y, which is less than or equal to 8,000, saying it will never reach 0 because it just keeps losing 25% of itself. If you explained that, I would buy that. I would buy your thinking if you weren't talking about whole bacteria. So as long as you defend yourself, that'll work. And the values of A and B, those just have to do with the function itself. So the value of A in this one was 8,000. And what do they tell me about the population? That tells me the starting population at time 0, when it began. And then the B value in this one was 0.75, and that is telling me, you got to come up with the words. What is that telling me? Because nowhere in the story did it say anything about 75. But 75% is the amount of the population that's left every hour, since it decreases by 25%. So that's where that came from. All right, so then you've got case B. Hopefully you did it by yourself. If not, why didn't you try that yourself now and pause this and see what you can get? And even if you did do it, if you need to adjust your thinking a little now that you saw the first one, then see what you can do there. So here's what I came up with. Jacob's studying culture and bio and notices the population started at 10,000 and it's decreasing by 40%. So it'll be 40% off what it was before. So if I take 40% away from the whole, I'll get 0.6 left. So 60% will be left every time. So that's the decay factor. And to test this out, I can take 10,000 times 0.4. That's the 40% it's going to go down by. So if I do 10,000 minus 4,000, I'll have 6,000 left, right? And that's what I've got here for the first hour. Now, if I take that 6,000 and divide it by 10,000 to just double check, my decay factor is 0.6. So if I just keep multiplying by 0.6 every time, you can test it out both ways, but make sure you get the same matching amount. So I keep it equals 3,600, 2160, 1296. Each time it's multiplying by 0.6, which I found out is my factor here. So it's times 0.6 times 0.6 to find that amount remaining every time. All right, so then my function would be the initial amount times 0.6 of itself every time, and then the domain is hours again, so anything greater than or equal to 0, and the range would be anything between 0 and 10,000. And again, I was considering that you have to have whole bacteria. If you were doing decimals and then you wrote an explanation and you did not put equal to here, and you said it could never reach 0, that's a fact about exponential functions. They won't ever reach 0. However, I decided that my explanation would be they only go, down. It'll get tinier and tinier and tinier, and you can't have half of a bacteria that's being counted in the population. So the values of A and B this time in the function were 10,000 for A. That's the starting amount. And then the 0.6, this part was what's left every time. So 60% of the population remains every hour. Or I could explain it decreased by 40%. So 1 minus 0.4 gave me the 0.6. All right, so similarly, Jackie's studying culture and biology. So see what you come up with for Jackie. If you're just still watching to check your work, you can keep playing or pause it to try it. There's something different about Jackie, so pay attention. So hopefully you realize that Jackie's is decreasing by 2,000 every hour, period. It's going down that exact amount. That is a constant rate of change. So this one's going to be linear. So it's not this formula anymore. Now it's going to be this formula for the equation. So y equals mx plus b. So I actually wrote mine as y equals b plus mx because I did the starting value and then the slope. So the population's pretty easy to figure out. It's going down exactly 2,000 every time. So you could use your equation and check it, make sure it works. You should do that on all of them. So this one, let's say I wanted to plug in hour 3, I should get 44,000. So if I put 3 in for x, just to check my work, I'd have 50,000 minus 2,000 times 3. So that would be 50,000 minus 6,000, which would in fact give me 44,000. So you can check your work. Same thing with these formulas. You can plug in your hours to your formula and make sure you're getting the right population. So you can make sure your formulas work. All right, so then the domain in this case is hours again. And so they start at 0 and go up. And then the range is the population, and I used my same reasoning that it could, that would eventually run out of bacteria. So you go down to 0. or you'd have a partial bacteria. Without context, we know that the exponential function will never actually reach 0 if you are going to be talking about pieces of a bacteria. All right, so then these are where a lot of the points come in on EA. Compare and contrast the functions. There's just a lot of things you can say, lots and lots of things. So you want to think about where they're increasing or decreasing, if they're exponential or linear, how fast they're decreasing, will they ever be the same as each other, things like that. So here's what I came up with. So again, lots of observations, but I noticed that case C starts the highest. It had 50,000 to begin with. All of these cases were decreasing. A and B were exponential decay, and C was linear, decreasing linearly. It had a constant rate of change. They will all eventually approach 0 because we're going lower and lower. And B decreases the fastest. It's going, at least at first, it goes down 4,000, where the other two both go down 2,000. And this one just keeps going down by 2,000 every time. So, so at the end, C, I didn't write this, but at the end, C is decreasing the fastest. At the beginning, B is decreasing the fastest. A and C decrease the same amount in the first hour, but then A decreases more slowly. So since these exponential ones are slowing down, they start off decreasing a lot and then they slow down. And the linear one is decreasing 2,000 every time. It's going to be decreasing faster towards the end, and these guys decrease faster. They're steeper at the beginning and a little bit flatter at the end. So stuff like that. Then it asks, will the cultures ever be the same, and how can you prove or disprove it? So all of the questions like this have lots of points tangled up in them, and it's your chance to explain what you really understand about these equations and these situations. So here are some of the things I said. I could make extensive tables or enter functions into a graphing calculator to see where they intersect. So I said yes, they'll be the same sometimes. And that would be where the populations were the same, where they intersect. So I could show you that on GeoGebra. So here are my 3 functions entered in like you learn how to do on GeoGebra. And I could see that obviously the linear one starts the highest. These two start the same. And then they decrease fast, but this one's decreasing slower at first and then keeps going and catches up. And if I zoomed way in, I'd see where it eventually crosses them somewhere between 20 and 30 hours by the looks. So yeah, that's a way I could defend my thinking. So now your the depth of your thoughts is going to be where you get all the points, and then obviously the accuracy of them. Don't say things that are wrong. Now on the EA itself, hopefully you've already worked on that a little. The ideas that we just covered in that prep are in there, but there's some different things too. So, be sure that you're aware of the questions and what they mean. She's studying a couple different cultures here and explains that A decreases 30% each hour and B decreases 20% each hour, and it shows the graphs. It shows a couple points on them, and these points are handy for a certain reason, for when you get to building your functions. But notice on number 1, explain. Number 2, explain. Then you have to write functions for A and B. So if I was you, after I wrote my functions, I would plug in this input and make sure I get this output. They should work. And then state the reasonable domain and range, and then use them to identify the values of A and B and what they stand for, like we did. Then she does 2 different cultures, C and D. So now you have to compare them and decide if they're linear or exponential. Hopefully you know how to do that. And then describe the similarities and differences between the 4 cases, like we did 3 of them in the prep. And then see what you think about Andrea's last statement here. But be sure you explain how she could prove it if you agree or disagree. Okay? So that's it. Prepare and think about what you want to say. Practice saying it. Make sure you don't get in the position where I know what it is but I don't know how to say it, because that's your job to prepare ahead of time. You're going to do great.